Greetings, everyone. This is Rithwik Sriram, and today I'll be giving a lecture on post-quantum cryptography under the computer networks subject. Right, let's start. Okay, since we had previously discussed about quantum cryptography in general, do check out the previous video. We'll here uh, again go through the basics summarization of what we discussed earlier. First one is, why do we need cryptography in general? Well, firstly, data travels through public networks, therefore it is quite unsecure, and there's a high chance of people intercepting such packets and your data as well. Right? Cryptography in general ensures confidentiality, integrity, and authentication, and it is something that now modern networks use quite predominantly, and it is something that I think we have all been quite familiar with, and I don't think I'd have to explain it much in detail. Right. Moving on to why quantum cryptography is the topic here. Why quantum cryptography is important, right? So there's a lot of threats with regards to how quantum systems work. Firstly, quantum computers use various types of, different types of physics. So there's a specific hardware that quantum computers used in order to decrypt the data that you encrypt, right? So it is quite easier per se for the quantum uh, architecture and the infrastructure to get a hold of the data that you encrypt, right? There's also the Shor's algorithm that we've previously discussed, and why quantum computing is a threat to modern cryptography is because it breaks the RSA and ECC encryption. So, which is, the elliptical curve cryptography. All of those things is generally now not secure since quantum computers have come into effect. Moving on, well, what are options? The first option is quantum cryptography. Previously, we had discussed about the quantum key distribution, wherein there's a key which is encrypted via the basic laws of physics using qubits, and how if somebody wants to eavesdrop into your conversation or your data, there's immediately the bit is flipped for the other. You via superposition, right? So that is something that was quite helpful, as we have previously seen, and why that quantum cryptography is generally considered secure. What is the other option? So the topic of today is the post quantum cryptography. Right. Within this, I'll just start. Okay, what's post-quantum cryptography, right? It's basically cryptography which runs in your current computers. It uses more advanced math rather than the quantum systems or the infrastructure that we have previously discussed. Right. Here, the it uses different type of geometrical or spatial mathematics, and it runs on current classical computers, which is quite a benefit since we don't have widespread infrastructure per se. Right. It also does not require a specialized hardware. So a hardware system in general will be much more important with regards to the QKD, which is quantum key distribution hardware, where you require the quantum computers in general to encrypt and decrypt your data. But here, in this case, your current mathematical models will be quite enough to completely encrypt. Why that is important is why we'll discuss forward. Right. What is the key idea here, right? So basically, the post-quantum cryptography, it replaces current RSA and ECC cryptographies, which is quite the standard right now. But since we have already discussed the quantum threats on how the current cryptography scenario needs to be changed, we'll now refer to the why post-quantum cryptography is quite important. Here, it requires a lot of geometrical as well as topological problems, which, when solved, gives you a specific answer by which your encryption and decryption happens. It is basically a resistant way for quantum algorithms to decrypt, right? So this sort of encryption is generally not quite into effect, but it is something that is quite promising within the current scenario. Moving on, it also provides a secure messaging platform wherein you provide. you can converse with other computers, other data points, or other users in general, while all of your data being quite secure. Okay, moving on. What is the major difference between a quantum key distribution and post-quantum cryptography, right? So, in basic sense, the principle that is used in QKD is quantum physics, as we've previously discussed. It relies on the natural laws of physics and how qubits or the data that you've encrypted is dependent on other packets, which is also qubits, using superposition, right? The PQC here requires newer sort of mathematics, which is technically derivable through the classical computers, which is a definite advantage with regards to the places where widespread access of quantum infrastructure is not present. Right? We also have the hardware-based differences where the QKD requires a specialized quantum device, whereas the PQC in general requires a normal computer set, as discussed. What is the purpose here, you might ask? Well, for QKD, the purpose is to secure your key exchange process, which is generally done in your RSA encryption or various other types of encryptions, where you have a public or a private key per se. Whereas in PQC, it completely replaces the RSA and ECC algorithms altogether. Since the elliptical curve algorithms, which we have previously discussed in the video, we discussed that how specific data points require a specific um, mathematical formula to derive the proper value in order for the key to in order for the data to be accessed, right? So that is now completely independent, now will be done independently via the PQC. What is the deployment difference here? Basically what happens is, for the quantum systems, there's a limited network access, right? Since there is currently a fewer infrastructure model, and it is something that is under development and will soon take place, but will take time. Right. For PQC, it is an internet-wide adoption, since it can be currently adopted as well as widely spread. Okay. Uh, Moving on. What is the types of PQC algorithms? Well, the first one is a lattice-based algorithm. The second is a hash-based. Third is a code-based, and fourth is a multivariate algorithm. Right. We'll not delve too deep into each of the algorithms here, but in general, each of the different algorithms provide a different mathematical model and structure for the PQC to handle. Right. For the first lattice-based model, it is basically dependent on geometric problems. Right. Uh, it requires relatively tougher calculations, which then ultimately provide more security to your data that is being spread. Secondly, it is even for a quantum computer, it is generally hard. So there is a misconception that quantum computers are something that can, pretty much decrypt anything. See, that is the difference. Assume that a quantum computer, a normal computer is a land-based car, and it works on like the better classical computers are faster cars. What is a quantum computer in that analogy? A quantum computer is basically a ship, so it completely works differently within the domain it's provided. So quantum computers work better within that specific domain, which requires the use of quantum computers. Not exactly all the problems that we currently have will be solved via the quantum computers, but it's something that solves a different set of problems itself, right? Example is Kyber. Kyber is a uh, current software which allows the lattice-based PQC algorithm to be used, and it is something that many companies like Google, Twitter, all of those are using, right? Moving on, we have why PQC is fundamentally secure. Okay, there are a few points here. Firstly, as I previously mentioned, it works on an existing infrastructure, right? So we have your computers in your colleges, in your homes, in your uh, daily life, the personal computers that you use. All of those already exist and have a specific computing power which can uh, easily run such algorithms which PQC provides. Whereas a quantum key distribution or a quantum cryptography based system will require heavy machinery, which is generally not accessible for the general public, especially with regards to the rural demographic in the country. Right. Then of course it is much more scalable for the internet since it can be easily transferred via one place to another through the existence of current network models, which is quite easy with regards to how it is used, right? There's no special hardware previously, as we've mentioned, and it has easier deployment. Right, the NIST, which is the National Institute of Science and Technology Standards of Technology, uh, is a US based standard system where the post quantum cryptography project is currently being undertaken, and newer algorithms including crystals, the Kyber, which I previously mentioned, is it's a key exchange project, right? Another under the crystals program is the dilithium, which is a digital signature for each and every node or computer that is currently joined in the network will leave a different digital signature, which is then encrypted into a particular way as provided by the PQC algorithms and then sent via the network. So it is much more difficult to open and to eavesdrop on, right? Moving on. Can PQC work under the current existing frameworks for the internet? Of course, it can. Right. As you previously mentioned, it is something that we are currently putting into production as per the NIST. It is quite informative, but it is something that will take time, right? So it can work over your HTTP, which is the Hypertext Transfer Protocol, the TLS, which is your transport layer security, which is a better version of the SSL model. You have the VPNs, virtual private networks, over which such the cryptography algorithms will be quite effective because that is something that you or me as a private citizen or as a employee of the government will require quite on a daily basis for your for the upcoming times, right? It is also provides a secure email and transfer like data messaging and transferable communication options, right? It also includes the authentication systems, which of course works under the current internet systems as previously mentioned regarding the RSA or the ECC based encryptions. Moving on, what are the current limitations, right? So there is this limitation with regards to how we use our current models, right? But what is the current limitations with regards to PQC, which we've discussed? Firstly, it requires more bandwidth, of course, since you have mathematical models to be used within your within our systems and different algorithms than the current systems. It requires a lot of bandwidth. It requires a lot of space within your systems, and of course, that will be a limitation with regards to how not every person will be able to fully utilize or optimize their systems accordingly. Moving on, we have larger key sizes. Here, since the mathematical models and the questions are quite hard to overcome, even for a quantum computer, the key size will appropriately be large and require much more information and data storage within your systems. There's a performance overhead since working on such large data sets will require a lot of performance from your PCs or your devices, which will of course cost a lot of overhead within your computers, be it your GPUs or all other sorts of processing units. Right. Moving on, we have the under research part where it is, of course, something that is still under research and it is not something that is widely used. It is something that we hope that we can use in the near future, but of course, a lot of research is still required. since as you and I know, it has not fully replaced our current performances. Then we also have the old plus new systems, which is, since even if there are newer systems which can overcome such limitations, which I've previously discussed, we still require the older classical computers to be used for the data transfer, for the internet-based encryption models, all of that. Therefore, it will technically cost more for us to provide provide a system where both PQC as well as classical computing encryption model work. Next, we have the part where the internet cannot switch instantly, since it has required the people of the internet to the netizens per se to switch from let's say Web 2 to Web 3 for such a long time. Similarly, for cryptography, it will not be easy, right? It will take more and more time on how PQC can be implemented.